Hello and welcome to Lecture 3 of the Sports Biomechanics lecture series, supported by the International Society of Biomechanics in Sports and sponsored by Vicon. So thank you to both ISBS and Vicon. If you haven't already, then I strongly encourage you to go back at some point and check out Paul Felton's lecture from earlier today on the biomechanics of cricket bowling, which should hopefully relate quite well to my talk, which will be on the biomechanics of cricket batting. So the last thing I'd want to do is to start a talk and then go on and take credit for other people's work. So I think rather than putting this at the end, I've chosen to kick off the talk with a bit of a thank you. Firstly, Chris Peplow on the left in the main picture of this slide. The majority of the research that I'm going to talk about today was part of Chris Peplow's PhD, so I have to give him credit where credit's due. And then credit also to Mark King and Paul Felton for their work on these projects when we were all at Loughborough University together, and more recently to James Grimley and Yash Deshpande for their contributions on this as well. And last but not least, the majority of the research was part funded by the England and Wales Cricket Board. Okay, so with any good biomechanical investigation into a topic, so cricket batting in this case, the first thing we need is a research question. And with this talk, I'm going to try and answer 3 questions. So try and get through them all in around half an hour or a bit longer. The first one, which I'll spend the majority of the time on, is what factors, or especially biomechanical technique factors, contribute to performance in cricket batting. Once we've answered that, we'll then take a quick look at whether those factors are the same for male and female batters or whether there are any differences. And then finally, once we know what technique's important and whether males and females use the same technique, we will look at how that can be coached within realistic training environments. Step 2 then, once we've got our research questions, is to come up with a dependent variable. That is, what is it we're going to measure that we want to improve or maximise about performance? To keep it simple, I'm essentially going to try and answer, how do players do this? So how do we maximise what I'm going to call carry distance, borrowing a term from golf? That is, how do players hit the ball as far as possible? There are many other shots we could have focused on, but if you take something like a drive or a pull shot, or anything of that variety, then we could potentially argue for days over what the most important variable is, what makes one person better than someone else, how do you decide what the best shot is. So we've kept it simple for now, and we've said if you can hit the ball further, then that's representing more successful power hitting, and we're going to look at what biomechanical factors cause people to hit the ball further. And to do that, hopefully together, we're going to build what's called a deterministic model of power hitting. That's a fancy name, but it's essentially a map of interrelated factors that all link together and contribute to maximising carry distance. So we're going to try and fill in the space below this with lots of different factors that all link together and cause people to hit the ball further than some other people. Okay, so what are these factors? Anybody who's studied projectile motion as part of sports science or biomechanics or even physics at school will hopefully recall that, ignoring air resistance, there are only 2 factors determining the range or the carry distance of a projectile. These are the angle at which the projectile is launched and the velocity at which the projectile is launched. And if we vary the launch angle and the launch speed of, in our case, the cricket ball, then we can get various different combinations of carry distances. So that's our first two parameters in the map, or the deterministic model. Carry distance is fundamentally and mechanically a combination of ball launch angle and ball launch speed. Hopefully making sense so far. Where I'm going to go now is to take each of these two in turn and look at what factors contribute to them. Starting with ball launch angle. According to some of our research recently, and again hopefully this is quite intuitive, almost all of the variation, around 83% of the variation in ball launch angle, can be explained by just one parameter, and that parameter is the angle of the bat when it contacts the ball. Hopefully makes sense that depending what angle the bat is at, the ball will then depart in a different direction. So slight simplification, but hopefully you get the idea. However, what angle should we be aiming for? Again, anybody who's studied projectile motion at any point can hopefully recall that for a projectile taking off and landing at the same height, so for example from the ground back to the ground again, the theoretical optimum is to launch at 45 degrees. For anything where you're aiming upwards, it should be more than 45 degrees to maximise the range or carry distance. For anything where the takeoff or release height is higher than the landing height, i.e. in cricket batting, where it's contacted at a point higher than the ground where it will land, we should be aiming for slightly less than 45 degrees. And when we put all of these parameters into a model, including things like air resistance, the theoretical optimum is to launch the ball at 42 degrees above the ground. However, when we've measured real people playing real cricket shots, so players ranging from club players through to full senior England internationals, their best shot, i.e. the one that they hit the ball the fastest, for people on average, was slightly less than 30 degrees. So we've got a clear difference between the theoretical optimal launch angle and the angle that real players are having success hitting at. This is where it gets a bit more interesting, and there's some ongoing research around trying to model why this might be the case. But a few ideas. First one we came up with was, could it simply be a case of minimising the risk of being caught? I.e. there's much less risk at a lower launch angle than a higher launch angle of the ball going too high up into the air, of giving fielders time to reposition and prepare for a catch. Or, and this stems from some of the work that the Loughborough group have done on gymnastics, around people self-optimizing to movement solutions that maximise their own margin for error. Could it be that this is occurring within cricket batting? I.e., if you were to play the shot at around 30 degrees, if you mistime it slightly, does that have less of a negative consequence than if you play it at around 42 degrees and mistime by the same amount due to the innate variability in human movement that we can't avoid? Again, a question that we're still trying to answer. Or could it be that due to either anthropometric, i.e. limb length requirements, or muscle capabilities, i.e. strength, that people are able to swing the bat faster at a lower angle and therefore hit the ball faster? Again, a few ideas around there. But, as I said, bat angle at impact is the key parameter for launch angle. I can now move over to the right-hand side of this diagram and start to look at, which may be a bit more interesting for some people, how do you hit the ball fast? And we've found the single most important parameter in this is the point on the bat face at which the ball is contacted, i.e. how close to what you might have heard referred to as the sweet spot. We've done a lot of research on this, and I'll link to one of our papers at the end, but essentially the common sense one-liner is that off-centre impacts result in slower ball speeds. We've managed to map this across the bat face, and you can see around the centre where the sweet spot is, we're getting a less than 6% reduction compared to optimum ball speeds, whereas towards the edges of that diagram in those red corners, the ball speed is reduced by over 30% for exactly the same bat speed and exactly the same incoming delivery. Because the ball has been contacted in a different part of the bat, we're seeing a reduction in ball speed quite significantly. And if we now split this up and look at both directions on the bat individually, we can see mediolaterally or horizontally across the bat face, we have highest ball speeds in the middle and then a drop off on either side. So off-centre impacts go to slower ball speed. If we look longitudinally now up the bat face, we see a similar thing. So sweet spot somewhere in the middle, which was around 17.5 centimetres above the toe of the bat. Either side of that, a significant drop off. So again, off-centre impacts result in slower ball speeds. And when we put both directions together, depending which paper we use, we're looking somewhere from 40 to 50% of the variation in ball speed between players and between shots can be explained simply by what the impact location is, regardless of anything else, as long as they're performing a realistic swing. When we now remove this aspect by focusing on only central impacts, so only impacts within 2 centimetres of the midline or the sweet spot, might be quite self-explanatory, but the most important factor is then bat speed at impact, i.e. the faster you swing the bat, the faster the ball's going to go. And there again, 83% of the remaining variation for those central impacts can be explained by bat speed. And this is where it hopefully gets a little bit less intuitive, but maybe a bit more interesting, is we can now look at what biomechanical technique factors allow people to do that. So allow them to swing the bat faster. To do that, we performed a study where we recruited 20 batsmen, ranging from club to, again, senior England internationals. They all performed a series of shots against a bowling machine. So here's a video example from a female participant in another study, but reflective markers stuck to joints all over the participant, including on the pads, including on the bat, and reflective tape on the ball. And we've then recorded this using 3D motion capture cameras, so Vicon cameras here. And that has allowed us to convert what the players did into a biomechanical model, a 14-segment model of their performance, and therefore get various joint angles and joint angular velocities that we can use to say what technique maximises bat speed. We measured 28 parameters, so some of them are on the screen now, such as how much front knee extension did they have, what was the bat angle, what was their stride length, their downswing duration, etc. And we measured all of these at 4 time points. The start of the downswing, the start and the end of the forward stride, and at impact as well. So what did we find? The single most important parameter of their technique that explains the variation in bat speed, i.e. why can some people swing the bat faster or slower than others, was something called X factor, which I know Paul referred to briefly in his talk earlier. That is the separation between the pelvis and the thorax in the transverse plane. Quick recap, Transverse plane is that plane through the middle of the body. Essentially, we're taking a bird's eye view and looking down on the batsman. If we draw a line through their pelvis and a line through their thorax or their chest, as they go to separate and rotate, those two lines will separate and form an X. The bigger this X, the faster players were then swinging the bat. So we're not simply talking about how far they rotate, it's the separation between the two segments. So how much further the thorax will rotate past the pelvis. And to display that another way, here we've got a red line through the pelvis and a blue line through the thorax, both mapped onto the floor. So it's this mapping onto the floor, looking from above, we're interested in. As the ball's released, there's no separation. We then get a separation or an X during the backswing, and it recoils and goes the other way during the downswing. No separation, separation, and then recoil. And the more that separation was, the greater the bat's speed. Essentially, this is because it allows batsmen to make more efficient use of the stretch shortening cycle, stretching the active muscles during eccentric loading to increase muscular force and power output during the subsequent concentric phase of the downswing. This leads to a faster uncoiling during the downswing, and we found similar separations to previous studies in tennis and baseball and golf. So tennis and baseball, but less than golf, probably because of the timing constraints, which mean players in cricket, tennis and baseball are having to respond to an oncoming ball of kind of unknown location and speed, rather than having a longer duration for a golf swing. Second most important parameter was how much did they extend their lead elbow. And then finally, how much wrist uncocking was there during the downswing. All three parameters together explaining about 2/3 of the variation in technique. With both the elbow and the wrist, we're saying not only did these maximize velocity, but extending them also maximizes the length of the bat arm overall system at impact. And a greater range of motion gives them more range through which they can accelerate the segment, which obviously then leads to increased segmental velocities and essentially bat speeds. What's interesting to me is that the order of importance of the three parameters goes from proximal to distal, i.e. from the centre of the body at the pelvis through to the elbow and then the wrist, getting slightly less important each time. So it's more important to get that initial movement right, which can then transfer through the body. This relates to proximal to distal sequencing, or a kinetic chain principle, which generally momentum will build up through the body from, say, legs, trunk, shoulder, elbow, wrist, with the velocity or force increasing slightly each time. And to highlight this another way, from our recent study in badminton, I've colour-coded the body segments based on their speed, and we can see this sequencing. As the player jumps, it goes down the body, and then as they go to swing, it comes back up the body, so that they've got maximal racket head speeds just at the exact moment of racket shuttlecock contact. So again, we see pelvis will go first, and then the upper arm, forearm, and finally the racket. So there are three parameters, again following that kinetic chain, starting at the pelvis through to the wrist. And so we can now look to answer our first research question: what factors contribute to specifically power hitting performance? Number one, you need to get the timing right so that we get the correct bat angle at impact, and we can also impact the ball close to the sweet spot. But once players are able to get that timing right, the bat speed then becomes the important parameter, where we want that kinetic chain starting with pelvis-thorax separation through to extending their elbows as much as possible during the downswing and finishing up with a maximum magnitude of wrist uncocking. So moving on quickly now, are these parameters the same for men and women? We performed a similar study to answer this one, so all of the same methods and analysis, but just 15 males and 15 females, ranging from elite university academies through to, again, senior internationals. It probably won't surprise people that, on average, males had a greater carry distance and swung the bat faster. But how did they do this? Well, when we compared men and women, the first two significant parameters were a greater X factor and also a greater recoil of the X factor in the men, but this time, rather than the transverse plane, it's in the frontal plane. So taking a front-on view this time. Rather than those lines on the ground, we're looking at the lines through the body from front on to the player. And it's this lateral flexion that causes an X to be viewed from looking front on that then recoils. And the men had a bigger X that also then recoiled further during the downswing. All of the other significant parameters, every single one that was different between men and women, related to elbow extension, again following through that kinetic chain from earlier. Men had a greater extension at both their lead and rear elbow during the downswing, which then meant by impact both elbows were more extended or straighter in the men. Our four most significant differences and biggest effect sizes all involved men extending the elbow more, and our single, by far the most significant and biggest effect size was the magnitude of lead elbow extension during the downswing. So I'll look at this in a little more detail now. Quite interestingly, on average, we see a clear difference here, where the average male player in our study extended their elbow by around 30 degrees, whereas the average female player flexed their elbow, only by a few degrees, but they flexed rather than extending. And we can go into more detail by looking at each individual player, because there are obviously differences between them. If I put the players in order, from those who flexed their elbow the most through to those that extended their elbow the most, with females in red, males in blue, we see this pattern. Hopefully you can notice that the 9 biggest flexion values all belonged to female participants, and the 9 biggest extension values all belonged to male participants, with 6 of each in that group in the middle. Or to split it along the other axis, not a single male flexed their elbow, whereas over half of the women did, or not a single male extended by less than 10 degrees. Whereas not a single female extended their elbow by more than 30 degrees, and over half of the men did. So there's a clear difference here on average. What does this actually look like? Well, to play both techniques, starting with the men, if you focus on that lead front elbow, during the downswing you can hopefully see it's extending, i.e. starts flexed now, then during the downswing it extends, whereas for the typical female, the lead elbow remains flexed all the way through the swing. Or for some females, they actually flex it even further as the swing goes along. When we compare this to other sports, the male technique quite closely resembles specific power hitting techniques such as golf. So it seems that they've developed a specific movement solution for the problem of maximising carry distance. And at least qualitatively, it resembles something like a golf swing. The females, on the other hand, seem to be, and this is an exaggeration here in this demonstration, but they seem to be utilising a more traditional movement solution for a cricket shot, but simply trying to increase the velocity and play that shot as quickly as possible. So it might be more of a checked drive, for example, rather than a specific movement solution for power hitting. What does this mean practically? Well, we're currently trying to answer, can the female players be coached to play the shot in the same way as the males? Or even, should they be coached to do that? Or are they limited by either anthropometric variables such as limb lengths or strength or muscular capabilities that mean that the constraints or affordances available to those players mean that they can't execute the same movement solution as the males? Interestingly though, in golf, we see the same male extension, female flexion pattern in experienced golfers, but in professional top-level tour golfers, we don't see that pattern, and both males and females extend their elbow, which suggests females can be coached to extend the elbow, although we must recognise differences in, for example, mass of a cricket bat compared to a golf club, or differences between a cricket ball and golf ball that may change the necessary capabilities in order to execute that technique. But within our study at least, the females who extended their elbow didn't actually swing the bat any faster than the females who flexed their elbow, so maybe we shouldn't be coaching them to extend. Or maybe elbow extension isn't important within the type of movement they're using. So it could still be possible that if they switch to a specific power hitting solution like that the males are using, extension of the elbow may then become important. But these are again more questions that we're trying to answer as we carry on in the coming months. Final question then, quickly to finish off. How to train these factors? Well, we need to recognise when looking at any training method that perception and action are always inherently coupled. The movements we do will always depend on the perceptual information available to us. And to look at this, we're going to look at an occlusion study. If you're not familiar with what an occlusion study is, I've got an example here of a football video using Cristiano Ronaldo from a documentary. And essentially, at various points during the ball flight, the lights are turned off. So lights go off, and he's then able to use early cues from body language of the kicker, as well as the early ball flight, to predict where that ball will arrive and to still contact the ball. And that is the exact same thing that this study has done, just in a slightly more safe and controlled manner for cricket. And we see, firstly, with no occlusion at all, both highly skilled and lesser skilled players are pretty accurate. Highly skilled, obviously, a little more. If you turn the lights out, in inverted commas, before the ball has even bounced, then both sets of players are still able to accurately execute the task. So therefore, they must be using information from before the ball bounces to do this. If we turn the lights off before the ball has even been released from the bowler's hand, the highly skilled players are still able to execute the task around 40% of the time. So it's clear that the elite players are able to use some information from what the bowler is doing in the run-up to inform their technique. And so if we want to train people to do this, we need to make sure we include it, that specifying information, within training environments. Various alternatives to a bowler that are sometimes used include a bowling machine, typically to reduce workload on bowlers. If you're not familiar, it looks something like this. No visual cues from a bowler, but the ball comes out of the machine in a similar manner. Or another alternative is something called a sidearm that might look a bit more like something you've seen used to throw a ball to a dog, but both coaches in the background of this video are using a sidearm.
Well, we're talking about the throwing device.
They're able to deliver the
also
ball
known as a wanger,
towards the
also
batsman,
known as another name.
and there is still more visual cues.
I've just got a bit of a theory on that. I think it's very false.
About what
you do pick up the cues of the thrower getting up into his action and ready to throw the ball, but
an early study into the differences between these three delivery methods looked at the time from when the ball is released to when players actually played their shot or started their movement. And if B for bowler on the right is our standard we're trying to recreate, then with the sidearm, people reacted later, either because the ball speeds are generally slower, even when you move the coach closer towards you, so they've got less time, they've got more time to react, or it could be because there's less information available, so it takes them longer to pick up on cues. But then the bowling machine, people actually responded quicker, and you can see from the error bars, some players actually responded before the ball was even released, because they're able to use information from previous deliveries to work out where the ball's going to land. So they're not actually responding to cues from that delivery itself. We've then tried to look at this in a bit more detail, and these are some really initial pilot results from a conference presentation I'm preparing for a few months' time. So I've just picked out a few highlights, but purely focusing on the upper body for now. In pull shots, we see at ball release, generally in order of how much visual information is available, with the least information available in the bowling machine, people pull the bat back furthest. With the sidearm, they pull it back a bit less, and the bowler the least, i.e. when you know there's going to be less visual information available, people are trying to limit or reduce the movement time necessary by pulling their bat back further before they even start. And then linked into that, against a bowler, when there's the most visual information available, people are able to initiate their actual movement soonest. We then see, starting with our kinetic chain from earlier, if we start with the X factor, it's bigger for bowlers, then sidearm, then bowling machine. So against a bowler, players are more able to use that proximal pelvis-thorax separation. Whereas if we then move along the chain to the elbow, the sidearm had the most back elbow extension. So it's kind of early results at the moment, but we might be able to say that against the sidearm, players are more elbow dominant. And then against the bowling machine, we have less action at the shoulder and more at the wrist. So potentially, moving along that kinetic chain, with the most visual information available against a bowler, we're pelvis thorax dominant. Against the sidearm, when there's a bit less information, our movement is limited, so we're almost starting with elbow dominance, and then with almost no visual information available against a bowling machine, players are wrist dominant. So we've concluded tentatively for now that the availability of pre-release cues affects upper body kinematics during the pull shot, and the sidearm might represent a compromise between the bowler and the bowling machine, but we should be aware of differences in that proximal to distal joint dominance. So back to our diagram from earlier, moving along that kinetic chain, if we want to train them to use that proximal to distal sequencing, maybe we need the visual cues available from a bowler, whereas sidearm might be more elbow dominant and bowling machine might be more wrist dominant. Obviously these are small differences. The techniques will still be largely the same, but some slight differences in dominance. And just to finish this off, some quite cool ideas recently of trying to get the best of both worlds. So limit the demands on bowlers and coaches, utilise all of the control that a bowling machine offers, but still include visual information so the players can learn to respond to that.
Well, today I've come into the indoor school at Lords
machine that includes the visual.
Well, today I've come into the indoor school at Lords.
And then the ball is
today I've come into the indoor school
at the same time as it would have.
Killer delivery. I think it's great that you can actually get that visual.
Okay, so I've been through all 3 questions quite quickly. Further information, if anyone's got any questions, then either leave a comment on the YouTube video or get in touch via Twitter or however, and I'll try and answer everyone's questions either individually or upload another video with responses depending how many questions there are. But for further information, the 2 main papers I talked about, the impact location sweet spot paper and the power hitting technique papers, are available, and if anyone can't access them, just get in touch with me and I'll see what I can do to help you out. And then finally, if anyone wants any of the references or the studies referred to, then they're all up here as well. And to finish off, if you well, hopefully you enjoyed that, but please go back and look at Paul's talk from earlier today on cricket bowling biomechanics, and then watch out next week for lectures on long jump with a sports prosthetic, and then the influence of running footwear on the 2-hour marathon, which will hopefully be really interesting. Thank you very much.